And we're back with acid, base, and pH calculations. This should be very easy. You can go through this fairly quickly, and then we have a little reaction prediction at the end because that's a really complex topic, and more practice will make you a perfect student in that realm. All right, so these are formulas that you should remember from Honors Chem. pH is equal to negative log of the concentration of H plus ion. If you have a strong acid and it gives you the concentration of it, then you automatically have the concentration of the H plus ion. If you're given a strong base and you're given the concentration of it, you are automatically given also the concentration of the OH ion. However, unless you have something like BaOH2, anything in group 2, there's a 2 subscript here with the OH concentration. So you actually need to times that by 2 before you plug it into this formula. So it's only, for example, calcium hydroxide, barium hydroxide, or strontium hydroxide. Okay, so that's whenever you have the 2 subscript, you multiply the concentration of the entire strong base by 2. Never, ever, ever do that with a strong acid. The only strong acid that we have that's diprotic is sulfuric acid, but you would never multiply it by 2 because of the fact that the first ionization is the only one that's considered strong. That's 100% ionization, while the second one sticks with the SO4 minus ion, or to make HSO4 minus. It does not ionize 100%. Okay, moving on. We've got our, if we know the pH, then if you take antilog of the pH, you can get back to the concentration of the H+. That's the same thing as doing 10 to the negative pH. Same thing with OH minus. You would have to have the OH or POH in order to continue with that and to get the OH minus concentration. Lastly, this is a really important one. pH plus POH is equal to 14. That should kind of resemble the 14 that we have here from the product ion constant, or the ion product constant of water, wherever you have the concentration of H plus and the concentration of OH minus equaling 10 to the negative 14th. Okay, and then this little note here is talking about the 2 thing I told you up here in the beginning. Down here we've got our acidic, basic, or neutral concentrations. We know if something's neutral, pH is equal to 7, okay, and also 14 minus 7 should equal to 7. That's using this formula here. The concentrations of the 2 ions in solution are equal, and they're equal to 1.0 times 10 to the negative 7th molar. Okay, and acidic concentrations, H plus is greater than OH minus, and basic concentrations, OH is greater than H plus. And we know that the pH will be in acidic solutions less than 7, and this one right here will be more than 7. This writing is lovely here. Okay, and in basic solutions, we know that the pH will be more than 7, and the POH concentration will be less than 7. And then the concentrations here will vary. It just depends on the concentration of the ions in solution. Okay, so we all know about sig figs. You know, you have to, when you multiply something together, then you need to count the number of sig figs, and the weakest link is going to kind of determine the sig figs left in your final answer. But with pH, the sig figs are a little different. The pH must reflect the number of sig figs in the concentration of the acid or the base, or the H plus or the OH minus. But when you count pHs, when you count sig figs in the actual pH, you can only count the decimals as sig figs. So the first number present is not going to be there. So this is just a weird rule. Okay, you need to know this rule whenever you're doing your sig figs and pHs, because we'll do it quite a bit here. All right, so if I want you to determine the pH, the POH, the concentration of H, and the concentration of OH minus, and you're starting off with nitric acid, 0.0025. Here, there's only 2 sig figs in the concentration, so your pH will have 2 decimals. So if this right here is equal to the H plus concentration, because you have an acid, you automatically say, okay, this is HNO3, that's a strong acid, therefore the concentration of H will be 0.25 or 0.0025 molar, due to the fact that HNO3, this is just a little background, HNO3 will ionize 100% to H plus and NO3 minus. So whatever you had number-wise here, you also have number-wise as NH plus and NO3 minus. And that's why we automatically assume the concentration of H plus is equal to the concentration of the strong acid. All right, to get the pH, you just take the negative log of the H plus number and 0.0025 molar. And that number gives you 2.60. And this is to 2, the sig figs are equal to 2 decimals here. So that's that weird rule, but this is our answer here because we have 2 decimals. All right, so POH is equal to 14 minus the pH because of the formula pH plus POH is equal to 14. Therefore, the POH is 11.40. Last thing to figure out is the OH concentration. The OH concentration is equal to 10 carat negative POH. Okay, this is just one way to solve it. You can do it another way. So when you plug the POH number in here, you get, which I actually didn't calculate. You guys can calculate that. You can do it this way, or you can take the KW is equal to H plus times OH minus. All right, you guys can get that. All right, so we have potassium hydroxide here, KOH, which is a strong base. So here we have the concentration of the base given to us. Therefore, we already know the OH concentration to be 0.021 molar. To get the POH, you take the negative log of the OH concentration, and that is 1.677. Okay, so looking back here at the concentration, we see there are 2 sig figs. So here, there can only be 2 decimals. So that's where our weird sig fig thing comes in on pH. So this needs to be rounded as 1.68. All right, and then the pH is equal to 14 minus the POH, which is 14 minus 1.68, giving us 12.32, keeping our 2 decimals here because this is just simply addition and subtraction. And this could be 14.00 actually. All right, then we have barium hydroxide. So I really recommend writing out your formulas because if you don't, you may not see that 2 here as a subscript, meaning we need to multiply the concentration by 2. So the concentration of OH is equal to 0.1018 molar. Okay, so you could easily make that mistake. Don't be that person that forgets to multiply by 2 for your strong bases here. So we get our POH by taking the negative log of 0.1018, and that number is 0.9923. I see 3 sig figs here, okay, because of the concentration. But when I multiply the OH concentration, that's 4 sig figs when I multiply by 2. So I'm going to be safe and keep my 4 sig figs here because this is technically the concentration of the hydroxide ion. Okay, I would give you some flexibility. If you put the 3, I would understand. All right, and then the pH here is 14 minus POH. Again, plug that number in, you get 13.077. And, 0.0077. Okay, and there's our 4 decimals there, which is our 4 sig figs in this case. Let's go back and reassess everything. Everything should correlate with our pH of acidic stuff is going to be lower than 7. pH of basic stuff is going to be greater than 7. So the pH here is 2.6. That's great because this is a strong acid. It's a really diluted strong acid. That's why it's not closer to 1 or 0. Here we have a base, and the base is somewhat diluted. Okay, when you look at your when you look at your pH, you see it's 12.32. That's fairly basic as well, almost 13, 14. We also have another base here. We've got the concentration, to be somewhat high for the OH concentration, which gives us 13, which is a good number because it's going to be highly basic. And you can double check yourself here. All right, so last bit here. If I want you to determine all of the concentrations in the POH of vinegar solution, vinegar is just a solution of acetic acid and water. So if I ever say vinegar, you should be thinking acetic acid. You guys can do this problem here where you take your pH and you get each of the other quantities. Okay, so you do this one. Next one is also for you. You've got your ammonia. Now ammonia is NH3. It's a weak base. So your number should correlate with that. If I give you the concentration of the OH concentration after the ammonia has been kind of reacting with water, it's going to produce some OH minus ions. That's how we get this molarity. I want you to calculate the pH, POH, NH+. I'm going to toggle back to the previous slide here. The reason that this pH is kind of somewhat higher for an acid is because our acetic acid is a weak acid as well. Just want to let you know that. So you're doing these two problems here. And here we go. Let's do a little reaction prediction together. This is the part I really want to practice because you're going to need to really understand how the terminology refers to how to write the right NIE. All right, so we have carbon dioxide gas, CO2 gas, and I like to write the state with it because I don't want you to make a mistake and forget that you don't ionize that, is bubbled through a solution of lithium hydroxide, okay? And this is solution, so I'm going to put aqueous. And when this reacts, you're going to have CO2 and OH kind of doing the switcheroo, okay? Because it's actually, we need to dissolve the CO2 in solution. We need to put it in its dissolved state. Its dissolved state is H2CO3. And then the lithium here is actually going to remain with hydroxide. So I actually haven't really done anything. I'm just trying to tell you that the CO2 needs to be put in its dissolved state before we continue with the double replacement reaction. Okay, so we've not really done anything. All right, now this is going to recombine with OH to make H2O, HOH or H2O, and the lithium is going to recombine with the carbonate to make lithium carbonate. Okay, and when you balance this out, you're seeing 2 lithium, so you need a 2 here for lithium, and we need a 2 here for water because we need 2 hydrogens and hydroxides. All right, so the weird part about this now is that we're gonna have to reassess the situation. So I'm gonna rewrite this. H2CO3 is aqueous. Then we have lithium hydroxide, which is a strong base, so it will ionize. So we have 2 lithium ions, and we have 2 hydroxide ions. Next, we have 2 waters, which are liquids, so we don't mess with those. Those stay liquid. And then we have the carbonate. In this case, it's a group 1A metal, therefore it is soluble. So 2 lithium 1+ ions and CO3 2- ion. Okay, so this right here doesn't break apart, therefore the carbonate's not going to be a spectator, but the lithium will be a spectator. But that's the only thing. So our final answer is the carbon dioxide in the dissolved state plus 2 hydroxides yields 2 waters plus CO3 2-. Okay, so this is a weird one because you have to kind of change around the original equation before you can actually do your double replacement reaction. Okay, next, sodium nitrate is reacted with hydrochloric acid. We're going to assume this is all aqueous because it doesn't tell us otherwise. So we get NaCl and HNO3. Looking at the situation, this is a soluble salt. This is a strong acid, soluble salt, strong acid. All of these will become ions. Therefore, none of them will remain, together. We'll neither have a precipitate nor will we have a gas, meaning we'll have no reaction. And just to finish this out, this would be Na plus NO3- plus H plus Cl minus yields Na plus Cl minus plus H plus NO3 minus. All of these cancel out, so you would say no reaction here. And the AP exam says they're not going to give any no reactions, but it's nice to be able to identify it for me, because you could see that on your test. Next is ammonium bromide and sodium hydroxide. All right, so we have ammonium, and hydroxide that need to come together. And we have sodium bromide. If you're looking at this one, you should be seeing that the ammonium hydroxide is unstable, and therefore it will further break down into ammonia and water. So here we go. I'm gonna take this out in just a second and put NH3 in water, but I'm gonna rewrite this. So NH4 plus Br minus. This is a soluble salt, therefore I'm ionizing it. And this is sodium plus and hydroxide. Yields, the unstable product breaks down into ammonia and water. Both of this is a gas and this is a liquid. Both of those are not going to be ionized, but the sodium bromide will. So we can cancel the bromide, we can cancel the sodium, leaving us with, I can't really rewrite this, I don't have no space. Ammonia plus hydroxide yields ammonia and water. So ammonium plus hydroxide yields ammonia and water. And that's balanced. Okay, and I like to leave the states there so it reminds me not to do anything with them. Solid magnesium oxide, so Mg2 plus O2 minus, is reacted with, let me put my solid there so don't forget, is reacted with hydrochloric acid. So we have a double replacement reaction occurring here. However, magnesium chloride does form. Okay, we all know that's aqueous because chlorides or halides are soluble. And we can put the O and the H together, but that makes just OH. And that doesn't make any sense. We need to make that into water. Okay, so any metallic oxide and an acid is going to make a salt and water. Alright, so then to balance this out, we put a 2 here with HCl. This is a solid, we don't mess with it. This is a strong acid, so we ionize it, distributing that 2 to both of the ions involved. This is a soluble salt, and 2 chloride ions, plus liquid water. The only thing that's able to cancel is chlorine here, and that's it. So then magnesium oxide solid plus 2 hydrogen ions yields magnesium 2 plus just 1 water liquid. All right. Alright, so these are not too bad. It's just making sure you know some of the exceptions to the decomposition of unstable products. Next one, equal moles of potassium hydroxide and phosphoric acid. Alright, so let's start off with KOH plus H3PO4. So we have an acid and a base, then you make salt and water. But it says equal moles. So if we have 1 mole of KOH and 1 mole of H3PO4, one of these hydroxides is going to pair with one of these H pluses. Okay, so only one H plus is neutralized from this. One H plus goes to water. Meaning, we know we have water, but this baby goes down to H2PO4 1 minus. When paired with potassium, it's H2PO4. That 1 minus crisscrosses down to the K subscript just to make a 1 there. So this looks funny, but we all know that it's possible. Okay, so the KOH is a strong base, so we ionize that. Phosphoric acid is not a strong acid, so we leave it alone. Water is just straight up water, leave it alone. And then this is going to be group 1 metal, so it will be ionizing to K plus and H2PO4 1 minus. Only thing that's able to be a spectator ion is the K plus, leaving us with OH minus plus H3PO4, yielding water, and H2PO4 1 minus. So this is kind of a hard one, so this is a really good one to study. Alright, solution of sodium fluoride, NaF solution, so there's our aqueous, reacts with diluted nitric acid. Right now this doesn't mean anything to you, the diluted word, okay? But we will talk about what it means a little bit more later in Unit 2, okay? So the sodium and the nitrate are going to come together. This is a double replacement reaction. And HF. So you know that this is a soluble salt. You know that this is a strong acid. Soluble salt, weak acid. So do not mess with the weak acid, leave it alone. Na plus and F minus plus H plus NO3 1 minus yields sodium plus and nitrate 1 minus and HF. So HF gets to stay together, leaving us nitrate goes away, sodium goes away, leaving us with F minus plus H plus yields hydrofluoric acid. Okay, that's pretty easy. Just got to know your 6 strong acids. Next, solutions of ammonium carbonate, or CO3. See if I can put this little 2 right here. I'm going to erase it on a space. Alright, let's try this again. Alright, okay. So solutions of ammonium carbonate and potassium bromide. This is a double replacement reaction again. When we do our magic, we get NH4Br plus K2CO3. soluble, 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 soluble. I really don't need to do anything else. Just to, maybe I should balance this just to make everybody know I do know what I'm talking about. So I balance this out. But since everything is soluble, I'm not even going to go through it. This is a no reaction because there's no bubbles, there's no gas, there's no precipitate, there's no heat, nothing. All spectator ions. Number 8, nickel nitrate. That 2 is going to be a subscript down here. And aqueous cesium hydroxide. Okay, cesium's in group 1. When they react, you get your double replacement reaction, so you get nickel 2 hydroxide and cesium nitrate, NO3. Just wanted to put that in parentheses for some reason. There we go, NO3. When you balance this out, you need to put a 2 in front of cesium because you're 2 hydroxide, and you need to put a 2 in front of cesium nitrate. Knowing now that hydroxides are mostly all the time insoluble, you should see that this is your precipitate, your nickel 2 hydroxide. So nickel here, nitrate, 2 plus, does ionize. So there's 2 nitrates, plus this hydroxide, which is soluble here, 2 cesium pluses, plus 2 OH minuses, yields insoluble product, which we don't ionize. It's our precipitate, nickel 2 hydroxide, plus 2 cesiums, oops, cesium 1 plus, plus 2 nitrates. You see here that the 2 nitrates are spectators, 2 cesiums are spectators, leaving us with Ni2 plus 2 OH minus, yielding nickel 2 hydroxide. Okay, so there's our final answer on this one. Just know your hydroxide rule. Alright, there's the last 3 here. Equal volumes. Okay, equal volumes of equimolar. That means we have equal moles, because volume times molarity is going to give us moles. Solutions of sulfuric acid and sodium hydroxide. Alright, so sulfuric acid is H2SO4 plus sodium hydroxide. If we have equal moles of these, then there's one, let's just say we have 1 and 1. 1 mole of hydroxide can neutralize 1 mole of H+, making 1 water, leaving an H+ with the sulfate here. So when the sodium combines with the bisulfate, I guess you could say, is the HSO4. Okay, this is liquid water. We don't mess with it when we start doing our ionizations. Just remember that you can only pluck off one of the H pluses whenever it's equimolar. So when this ionizes, because it is a strong acid, H plus, HSO4 minus, plus sodium plus hydroxide yields H2O liquid, and the soluble salt does ionize. Now this one's cool because this does cancel. The bisulfate ion cancels, the sodium ion cancels, leaving us with just the elements that will combine to make water. We don't see that too often, so that's a good one to study as well. Alright, last 2. Solid cobalt 2 hydroxide. So here's cobalt 2 hydroxide and hydroiodic acid. When these recombine, you got an acid-base reaction, neutralization here. We know we have to make water and cobalt 2 iodine. Here, this is not a strong base, okay? This is a weak base. This is a strong acid, so we will have to ionize that strong acid. The liquid stays, and then this is a halide, and most halides are actually soluble. Even though it looks weird, we haven't seen that before. It's aqueous. So this is important. Keep your cobalt 2 hydroxide together. Your H and I come apart. Your water stays together, and your cobalt 2 and iodine, 2 iodide ions will come apart here. So, oops, I didn't balance it before we started. So this 2 for the I should come in front of this hydroiodic acid. There's a 2 here, so I need to put a 2 in front of the water and 2 hydroxides. Okay, so let's carry these 2's down where I forgot. Here we go. 2, 2, 2. The reason I saw that is because I saw there were 2 iodines here, and I knew I needed to cancel them, so you can usually check your balancing with the NIE as well. and everything else stays. So our final answer would be COOH2 plus 2 hydrogen ions yield 2 waters plus cobalt 2 plus ion. Alright, so aqueous solutions of potassium phosphate and excess, I'm going to put the top, hydrobromic acid. Okay, this is important because when we say excess usually indicates that you're going to have a lot more than you need. So if there's any extra neutralization or extra reaction that needs to occur, there's enough hydrobromic acid to do the job. Alright, so let's just do our double replacement. I'm sorry, this keeps coming up. Okay, so the phosphate and the hydrogen are going to come together to make H3PO4, and the bromine and the potassium come together to make potassium bromide. 3 here, so I need a 3 here. Bromides, 3, and there's already a 3 for the potassium, so we're in good shape. And this is aqueous, and this is always aqueous as acid. This is not a strong acid, this is a weak acid, and this is a soluble salt. So now we can actually ionize everything, so 3K plus phosphate plus 3H plus 3 bromide ions yields H3PO4 because we keep that together. It's not strong. Plus 3K plus 3 Br minus. The Br minuses can cancel. The K pluses can cancel, leaving us with PO4, 3 minus plus 3H plus, yielding H3PO4. Okay, so you don't always have to write the total ionic equation, which are the middle steps on all these. If you can see what's left and you can see the final NIE, you know, kind of take a second to think about it, you can totally go through and do the NIE. You don't have to, I show all my work for you, but you don't always have to for me. I like to give you partial credit where it's due, so if you can always get extra credit. Alright, so you have those 2 pH problems before, and you have these 3 NIEs I need you to do. If you have any questions, we'll go over them tomorrow. Be sure to ask me about them if you have any issues, and have a lovely evening.